the Doppler effect. This is an effect that many of us have observed, probably all of us have observed, but we may not have known exactly what it was all about. With the Doppler effect, when the source of sound is moving, then the sound that we hear as the stationary observer can change. And one of the most common examples of this is when a car is going by and honking a horn, or if we hear a car with a siren going by, we hear the frequency of the sound changing. So as a car drives past you on the road, if they honk their horn, it might sound like this. That's probably the best imitation I can do for the Doppler effect, so my apologies. But I think we've all heard a sound something like that with cars going by on the road, or a car with a siren. And so as the source of the sound approaches us, we hear the high frequency sound, the hee, and as the object goes past us, the frequency drops as it moves away from us. So hee, we get that low frequency sound once it's moving away. So if the source of the sound has a frequency which we call f, and it's moving relative to the observer, then the frequency will be greater than f when the source is approaching and lower than f when the source is moving away from the stationary observer. So here's a diagram that explains, helps to explain why this happens. If the source is at rest, then the sound is going to travel away from the object in all directions pretty much equally, which means that the crests, if you will, or those compressions in the sound waves are all the same distance apart, so they'll strike your ear with the same frequency. In other words, the same number of compressions will strike your ear each second, whether you're in front of the vehicle or behind the vehicle or above or below. But when the source of the sound is in motion, then in front of the vehicle, those sound waves tend to kind of bunch up, so the compressions get closer together, because in a sense the vehicle is catching up to the sound waves. Unless it's traveling at the speed of sound, it hasn't caught up to the sound waves, but in part it is catching up, and so behind the vehicle or behind the source of the sound, when it's moving, those sound waves stretch out a little bit, and you get those compressions further apart, which we can see on the left-hand side here. So here in front, the compressions tend to get closer together as the sound waves sort of bunch up, so that if you're standing in front of the vehicle, those compressions, more of those compressions strike your eardrum each second, so the frequency will be higher. And back here, these sound waves, because these compressions are more spread out, then fewer compressions will strike your ear back here each second, so you hear a lower pitch sound or lower frequency sound. The sound that we hear, which we'll refer to here as f2 in the formula, can be calculated using the formula, where f1 is the true source of the sound from the vehicle or from the moving object that's emitting the sound. And Vs is the speed of sound, and Vo is the speed of the object. You'll notice there's a plus or minus here in the denominator of the formula. The plus is how we will use the formula if the object is moving away, if the source is moving away from us, and the minus will be used if the source is moving towards the observer. The reason for that is that if the source is moving towards the observer, we know that the observed frequency f2 will be higher, which means we need a smaller number in the denominator because we need to divide this value by the smaller denominator to get a higher frequency. So that's an easy way to remember it. So f1 is the true frequency of the sound measured in hertz. f1 is the frequency of the sound as it's heard by the observer, also measured in hertz. Vs is the speed of sound, and Vo is the speed of the object or speed of the source. Those can be in meters per second or kilometers per hour or any other units for speed, but they must be in the same units. Let's try an example. A car traveling at 25 meters per second away from the observer at 0 degrees Celsius honks its 240 hertz horn. What is the frequency of the sound heard by the observer? So we'll use our formula for the Doppler effect. F2 equals F1 times the speed of sound over the speed of sound. And in this case, the object is moving away from the observer, so we'll use the plus in the formula. So we'll substitute in the values. There's our plus since the source of the sound is moving away. And we get 223 hertz. So that means that if I'm in the car, I hear a sound of 240 hertz because I'm moving with the car. But because the car is moving away from the observer hears the lower frequency, and that's the Doppler effect.